Welcome to the 6th BayesiaLab webinar this year. My name is Stefan Conradi and I'm the Managing Partner of Conradi Applied Science, and I have Dr. Lionel Jouffre with me joining today from his office in France. Lionel is the CEO of Bayesian SAS. I'm delighted to see that we have once again so many people joining us from all over the world. Looking at the list of registrants, I think we have folks from all continents around the world with the exception of Australia, but that's perhaps understood because it's rather late in the day for them. Anyway, let me give you a quick overview of what we're planning to do in today's webinar. So here's the overview. I'd like to start things off with a quick introduction about us, our partners. Then I'll start framing up the topic of today, knowledge discovery in the stock market. We'll talk a little bit about some traditional methods that have been used in the past and are still being used for multivariate time series analysis. I will then introduce our specific topic, the S&P 500 index. From there, we'll go back a little bit to the basics and talk about Bayesian networks as the framework for our analysis work, and then we'll talk about the tool, our software BayesiaLab, and from there we'll go into the specific introduction. Even though this list looks longer than Lionel's list, the actual focus of the webinar will be on the tutorial and the BayesiaLab software demo. Let me now introduce our topic of today, knowledge discovery in the stock market. And perhaps the first thing I should say is what this webinar is not. So for those of you who hope that we will unlock all the secrets of the stock market and how to make lots of money, I'm afraid I'll have to disappoint you. This is not what this webinar is all about. However, what we want this webinar to be about is an example of how we can try to understand a highly complex, high-dimensional problem domain. And I think the stock market is a perfect example just because of the myriad of variables and interactions. So, and the research method that we will present today is actually not specific to the stock market. It's just one very good example. But you'll find that what Lionel is going to present in the tutorial could just as well be applied to biostatistics or marketing science or many other fields of study. Feel free to go on our website. You will actually find several other examples on these other fields of study. So, knowledge discovery. What do we mean with knowledge discovery? It can really cover a lot of things. And as we try to understand a domain, we can take a sort of a very basic approach through human learning. We can study charts, graphs, tables, and implicitly build a model of the domain in our head. So, for instance, here we would study the trends, the curves, the peaks, the troughs, and so on, and try to absorb what is happening in the market. Or alternatively, we can create a more formal model. We can derive a statistical model that describes what we observe in the market with all these observations. So, and I want to quickly cover, but before we go into our new approach with Bayesian networks and BayesiaLab, I want to spend just a few minutes on traditional methods of learning about time series, measuring interactions, and so on. And here's just an example of what one would typically do. I've selected 4 stocks: Procter & Gamble, Clorox, Colgate-Palmolive, and Johnson & Johnson. And I've taken a fairly typical approach that one would take to understand the interactions of these stock prices. I would start off with plotting the levels. I would take first differences of the logs of the prices. I would perhaps create a cross plot between individual time series. I would look at autocorrelation plots just to get a sense for how these time series relate to each other. to get a more formal understanding of how they interact, I may want to estimate a vector autoregression model. This is a very practical method of seeing how one time series affects another, not just between two time series, but actually between multiple time series. So here, for instance, I've taken 4 time series at the same stocks again, P&G, Clorox, Colgate, and Johnson & Johnson, and estimated a model that describes how these time series interact. With such a model, then, I can compute an impulse response analysis that then tells me what happens if I introduce a shock on one variable and how that goes through the system and affects all the other ones. But there are unfortunately quite a few limitations on this traditional method. First of all, we're limited in terms of how many variables, how many endogenous variables we can include. Here we have just 4, which is quite manageable, but if I went to 10 or 15 or 100, things would become quite difficult to estimate. I mean, we would simply run out of computational resources, and we may have a over-parameterized systems. We may not have enough observations to really estimate all the parameters. And, which is a very, very important limitation with this particular approach, we'd have difficulties estimating the contemporaneous relationships between individual variables. So, and again, with 4, it is somewhat manageable, but the reality of the stock market is we have quite obviously a lot more than just 4 variables. We have a dizzying array of stocks, bonds, exchange rates. We have different stock exchanges around the world that operate at different times. So how do we make sense of all this? How do we even start an exploration if we realize that our traditional methods really can't capture the whole thing at the same time? And our approach here is machine learning. We want to use machine learning for knowledge discovery instead of us poring over charts and graphs and trying to make sense of it in our brain, or instead of trying to fit small local models to some elements of these variables. We want to look at as much of it at the same time as possible. So how do we go about this? What's our approach? Let me introduce our example here. Instead of 4 variables that we used earlier, we want to use 500 now. This is sort of a good sets for our exploration purposes. All of you will be familiar with the S&P 500. Just a quick recap. These are 500 large cap stocks that are actively traded in the US. And these stocks can be traded either in the New York Stock Exchange or on the NASDAQ. So for the stocks in this particular index, we've tracked all of them over a period of 6 years. So we really have daily prices for these stocks over 6 years. Actually, it's a few less than 500 because there were some stocks that weren't traded consistently over this entire time period. For instance, GM, AIG, which dropped out at some point. We have excluded them, so we have a total of 467 stocks. And over 6 years, that yields us 512 observations. So this now serves as the basis for our further exploration. And let me put this into context, and this is where the Bayesian networks come in. We have all these observations, all these time series, and we want to apply machine learning for knowledge discovery so we can extract a pattern, interdependencies. And this machine learning, this knowledge that's generated, will turn into a Bayesian network. And the Bayesian network then becomes our new representation of the knowledge that's contained in the system. So it's a new form of knowledge representation that can then serve us for decision support, for analytics. We can, in this case, of course, use it for investment decisions, and so on. However, today we don't want to talk a lot about interpretation and analytics. Rather, we want to look at how do we discover this knowledge? How can we find out about all the interactions that are going on in the stock market? So far I've only talked about Bayesian networks in theory, but they have such central importance to us as a form of knowledge representation that I need to just recap a few of the basics. Once we're done with that, I'll return to our principal example. So what is a Bayesian network? I think the easiest way to explain it is just by an example. Imagine we took a survey of all participants in this webinar and asked about their hair color and their eye color. We would look at two random variables that represent the distribution of eye color and hair color. In the Bayesian network context, variables are represented as nodes. Here they are symbolized as blue dots. So, for instance, now if I were to ask you, chances are we'll probably have a marginal distribution of eye color like this: brown, blue, hazel, and green. And now this particular marginal distribution relates to the overall population, I believe. And so the marginal probability of having brown eyes would be around 37%. Now, looking at hair color at the same time, we can also look at the marginal distribution of hair color, but more importantly is the conditional distribution. Given that I have a certain eye color, what is my probability of having a specific hair color? So one example would be, given that the eye color is brown, the conditional probability of black hair would be 31%. So you may say, well, what has this got to do with anything? This is so simple, I could just do this in a spreadsheet. Well, you're absolutely right. This is very simple. For this example, we don't need a Bayesian network, but let me explain how a Bayesian network can simplify things, because this contingency table that we have with the conditional probabilities, this is encoded in the arc that connects the variables. So in a Bayesian network, whenever you see an arc, this arrow, this means there is a contingency table that can be either two-dimensional, three-dimensional, can be a hypercube that links the variables, the nodes, with each other. So, as I said, this is still very simple. We don't need a Bayesian network for this, but more common is a much more complicated network, because in our observations we have many more variables. And this, for example, is a network that represents a consumer survey. This was conducted in France. 1,000 women were asked about their liking of perfumes and fragrances, and then we learned a network that represents the joint distribution of this entire consumer survey. So, but that's not our topic of today. I've now given you kind of the Bayesian network framework. What is our paradigm? Now I want to briefly touch on the software we're going to use. This is BayesiaLab. This is the software we're promoting and selling. This is our knowledge discovery tool. So BayesiaLab becomes our platform that does everything from learning Bayesian networks, editing, making inference, analysis, simulation, all in a single user-friendly platform that's available for Windows, Mac, OS X, Unix, Linux, you name it. It's a very, very universal tool. And Lionel will very shortly use BayesiaLab to then go through all these learning and analysis steps. So now back to our example. Now specifically, what are we doing? I'm now taking our data set, preparing it for BayesiaLab. As I said before, we have these 467 stocks. Of course, we show a lot fewer here on our screen. I think there are only about 36 on the screen. And they show us their values over the entire 6-year period. However, we're here not so interested in sort of the long-term trends and the long-term swings in values. Much rather, we want to see how these stocks interact within a very short time frame. And so we take the log difference and compute the daily returns. The log difference here stands for or represents daily return, and so we're computing this for the entire set of 467 variables, and that then provides the basis for our learning with BayesiaLab. With that, I would like to turn things over to Lionel, and I'd like to really iterate here. We're focusing on our tools. We're not so much interested in what can we learn about the stock market per se, not giving you investment advice, but much rather we would like to demonstrate some very, very powerful new methods which will then allow you to generate new insights and explore this topic much, much further. So let me make Lionel a presenter.
So as Stefan said, I will first describe very quickly what will be the steps I will describe in much detail. So we will analyze this data from this SP500 by using BayesiaLab and just generating mainly unsupervised learning and semi-supervised learning algorithm. So let's go there with a mind map as usual, just to be sure that every step will be clearly understood. We will first, as this is a data mining task, we will use our data importation wizard that will allow us to define the data structure, and in that very specific case it's a text file and it's a CSV file, and you will see that we will be able to describe is this text file is separated with semicolon or comma or spaces, or you can define whatever you want. We can define samples, we can define typing. So as you can see, we have a lot of possibilities, and we will use the first line just in order to name automatically the nodes. Okay. Then we will use the second wizard in order to define the type of the variables, and in that example we just have continuous variable. So we will need to discretize those discontinuous variables, and to do that we will either we can use manual discretization or k-means, and I will show you how we can first of all just focus on the continuous variable, one of the continuous variable, then select the manual discretization just to have a look of the probability of the density function, and then we can either choose threshold by hand or we can use automatic discretization algorithm even when we are in the manual discretization. And we will, in that example, choose the k-means into 5 states just to find, best discretization according to the probability density. Okay, then once we will load all the data into BayesiaLab, we will do, first of all, a maximum weight spanning tree, just to have a quick look, a quick understanding of what are the relationship between those variables. So we will have this kind of result, and it's not so easy to understand, so we will use we will be able to associate comments in order to associate name to all our variables, and we will use our automatic layout algorithm just to be able to display that tree in a much easier way to understand. And once we will be there, we will take just a few seconds to focus on two companies, P&G's first one, just to see what are the neighbors of P&G in that broad set of variables, of that bunch of variables. And we will also have a very quick look on Apple, just to see, as we are working with Apple here, just to see what are the neighbors of Apple in the stock markets. And we will then, as we have really a lot of variables, it's 467 or something like that, we will focus our analysis then on PNG, and we will do what we call semi-supervised learning, meaning that we will first define PNG as a target variable, and we will do new node selection based on recursive Markov blankets, and then we'll select the Markov blanket of PNG, and then the Markov blanket of the nodes belonging to the Markov blanket of PNG. And once we will select the nodes with that new methods, we will be able to do unsupervised learning on a subset of nodes. We will have, if I remember well, 67 or 70 nodes like that. We'll do a SOP-like just to have an unsupervised view of that network. And we will do a neighborhood analysis just to focus on the relationship with the length that is from 2. We don't want to be far from more than 2 links between Procter and Gamble on the other nodes, and we will end up with that kind of network. Then we will use that subset of nodes to illustrate how we can do cross-validation to help choosing what is the best structural coefficient. I will just say a very quick word on that. This is parameters that allow us to play on the structure, on the trade-off between structural complexity and the likelihood of the data. And so we will just generate this kind of curve where we will be able to apply the elbow rule and just select here, for example, a structural coefficient of 0.45. And then we will also use another kind of cross-validation technique in order to evaluate the confidence we can have in the arcs that have been learned. And we will first do that with the jackknife, and then we will also do that with data perturbation algorithm. And we will be able to generate this kind of graph, which is here. It's not a Bayesian network, it's just a graph that depicts what the thickness of the arc are directly proportional to the frequency of the arc generated during the cross-validation. And once we will do that, we will be able to just select what are the nodes that belong to the Markov blanket, but we will take the maximum of the Markov blanket. That means that we will also add nodes that just appear in some network generated during the cross-validation. Okay. And then we'll save that new network, and it will allow me to show you how we can associate the data to an existing network. So we will illustrate data association, and then I will use the temporalization. This is a new function we just had in BayesiaLab 5.02, and that allows to duplicate nodes, and we will have this kind of result. We'll have for each node 20 temporal clones, and then we have here 21 nodes for PNG, 21 nodes for Johnson & Johnson, and so on, and we will learn relationship among those nodes. We will define our constraints just to forbid contemporaneous relationships, and we will make a first supervised learning just to see what is Markov blanket now of Procter & Gamble, by just trying to predict what is the value of Procter & Gamble at t plus 20, and we will see that it depends on Procter & Gamble at t plus 19 plus t plus 10 and so on. And we will end up with an unsupervised learning on the same data with SOP-like, and we will see that we will find different subnetworks, and we will focus just very quickly, if we have some time, on that one, which is very, very interesting here. It's a Kimberley-Clark, and we can see that Kimberley-Clark just depend on Kimberley-Clark just the time step before, whereas other networks like that one, we have some mixed. We have PNG, we have we have Clorox and so on here that are mixed. But just now go through BayesiaLab in order to show you how everything works. Okay. So, as I said at the very beginning, I will go there, data, open data source, and select my CSV file, which is here the SP500. I will open it, and I have my first result. As you can see, this is exactly the same thing as I showed you before, so I will just very quickly go through that result. And every variable here is continuous, so it's depicted in blue-green here, no discrete variables, so I'm just going there. We don't have any missing values, so we can skip that result too. And now this is the result that will allow us to carry out the discretization of our continuous variables. So if I'm just select this one, A and D, I can go there, manual discretization, and I will have that function that represents it's a view of the probability, the repartition of the data of the continuous value. And I can switch the view just to be able to have the density function of that variable. And we can say, for example, well, we will add a link there, a threshold here, for example, and another one there. Or we can just use our automatic discretization algorithm. So, for example, I can click here on generate discretization and select k-means 3, for example, and I will have, this is the advantage of that k-means, when the data is almost normal there, we can have one threshold for the two tails and a big one, big bin for the model values. And in that example, I will indeed use k-means, but with 5 states. And in that case, we can have, we will have a better definition. And I will not do that variable per variable, so I will just select all the continuous variable and then select k-means into 5 states. Okay. So I will discretize 467 variable with that discretization algorithm. So here, as you can see, it will take, I don't know, 20 seconds just to carry out that discretization. So we are just taking one variable per variable, applying k-means algorithm in order to find what are the best thresholds in order to fit the density function of each of those continuous variables. Now we are creating the database, and here we have the Bayesian network that correspond to that data. So I can select every node, and we have 459 variables. And as I said before, I will first carry out an unsupervised learning called maximum weight spanning tree. That will it will build a tree, so it's a constraint-based algorithm because we don't want to find a more complex structure than a tree, but the advantage it's very quick to learn, because here with 400 nodes, if we don't use that kind of algorithm, we can spend minutes for learning a network like that. So if I'm just focusing, as you can see, it's not so readable, and one of the quality of Bayesian network is that you can quickly see, quickly discover the knowledge that is hidden in database. But if you just keep with the network like that, you will not be able to understand anything. So this is the reason why we have some powerful layout algorithms that will allow you to quickly find the best layout for your network. So I'm just going there, view automatic layout, and choose force directed layout, and I have that result. And then I can, if I want, I can select a subset of nodes and just select here best fit. And I have, as it's a tree, it's very easy to understand. But first of all, I will associate a dictionary just to have some full name, because I don't know if you are used to those stock names, but I am not, so I will have to use a dictionary just to be able to quickly understand what that means. So I'm going there, the name. So it's a text file where each node, for example here, we will have in that text file TLab, and then a tabulation, and then we will display directly the name, which is TLab's incorporation. Okay, so we have that for all the node, and as I said, I will first try to find where is PNG. So I'm using the find the search function here, and I will type PNG and press return. Here by clicking on that node, on that line, I will highlight my node, and I can just by doing that focus on that area. And as we can see, P&G is close to Colgate, is close to Johnson & Johnson, is close to Kimberly-Clark, to Kellogg, and General Mills is close to Kellogg, Campbell Soup is close to Kellogg, and so on. So that perhaps you just think, well, it's obvious, but when you are not used to those companies, those American companies, it's a new knowledge. And you just, as Stefan said at the very beginning, if we take data coming from, microarray or market research or whatever you want, you will quickly see those kind of relationships that just can seem very obvious when you know the domain. But very quickly, by using that kind of tool, you can get some, obvious knowledge for people who are working on that area since a lot of years. As I said before, also I will very quickly have a look to Apple, just saying. So in that search tool, I can just use star just to say, well, I know that the beginning is AA, but I don't know the end of the word. So just I'm clicking there, and I can focus on Apple there, and just see what are the neighbors. And we have Apple, Yahoo, Google, eBay, Amazon here, and this one is Packard Incorporation. So I don't know, it's not an interactive session, but if you have any question, you can just focus, say, well, where is the company I'm looking for, and you can have a very quick look like that. Even if we are working in a very huge hypercube, because we have 400 dimensions. So now I will come back to P&G. Here, this one, and I will define that node as a target node. So I can just press T and double click, or just make a right click on the node in order to activate the contextual menu and just select set as target node. Once I have that target defined, I will use semi-supervised learning, because my goal now is just to try to reduce the search space. I just want to focus on the companies that are related to P&G. So I will go in learning, target node characterization, and I will choose a semi-supervised learning. That algorithm will ask me the depth I want. So indeed, it's based on our Markov blanket learning algorithm. I don't know if everybody knows that algorithm. It just consists in finding what are the parents, what are the children, and what are the spouses of each node. Given that when we know the values of that Markov blanket, then we don't need any information on the other nodes, because we have that blanket, and then all the other nodes are screen off given that Markov blanket. So in that algorithm, it's a kind of a new kind of selection algorithm, if you will. We are first trying to find what is the Markov blanket of P&G, and then for each node of the Markov blanket of P&G, we are also learning the Markov blanket of those nodes. And if I can change that. If I set 3, I will also learn the Markov blanket of the Markov blanket of the Markov blanket of P&G, and so on. So it's a recursive algorithm. But here I will just focus on a depth of 2. And it will be very quick. At the end of the day, I have a set of nodes that have been selected. I can go to Edit and then go to Invert Selection of the nodes. Then I will select all the other nodes, and I will delete those nodes, just because now I want to just focus on the nodes that are close to P&G. As you can see in the lower right corner, I have 391 nodes that will be deleted, and I will just press on Supreme, on Delete, and I have my new set of nodes. And now I can use more sophisticated algorithms than the maximum weight spanning tree. I will use my Subtree here, which is another algorithm than EQ that we are using all the time. So now we are just using Subtree, and we will find the relationship among all those variables. So I can just go View, Automatic Layout, Force Directed Layout in order to have this kind of view. I can even now, I guess, press on M just to display all the comments. And we have there the a network that corresponds to the large neighborhood of Procter & Gamble. But as I said at the very beginning, I'm just interested in finding the nodes that are close to Procter & Gamble, and the neighborhood I've defined is 2. So I will, in order to select only the nodes that are close to P&G, and when I say close, it's maximum 2 links, I will go to F5, my validation mode, there, by clicking there, or directly you can go in View validation mode, and I will use the graphic. What happened? Oh, sorry. I press on genetic algorithm for layouting. Okay, there, and I will select graphic node neighborhood analysis, and I will try to find where is my Procter node. It's here. By clicking on Procter & Gamble, now I have the Markov blanket of that node, because I have just selected Markov blanket there. But as I said before, I want to select the neighbors with depth of 2, and then I can click here, and I have just all the nodes that are linked to Procter & Gamble with a maximum of 2 links. And I will select all those nodes just by pressing Ctrl+A. So all those nodes are selected. I'm just killing that, going back to modeling mode, and I will again invert the selection in order to delete the remaining nodes. And now I just have what we call the semi-supervised learning with depth of 2. Okay, it will be more easy like that. And as I said in my introduction, I want to use that little network. Now we just have 30 nodes to show you how we can use cross-validation. For example, the first thing we will do is, can we change the structural coefficients in order to obtain a more complex structure? Or is it worthwhile to have more complex structure? Just in a few words, the algorithm we are using in order to build those networks are based on what we call the minimum description length. So it's a score-based methods where, and this score is twofold. The first part of that score is based on the complexity of the structure, and the second part of that score is based on measures the likelihood of the data given the structure. And then we have introduced a parameter which is called here the structural coefficient, and that allow us to handle the trade-off between the structural complexity and the likelihood of the data. So if I set, for example, the structural complexity of 0, I will find a fully connected network. And if I set a structural coefficient higher than 1, then I will be highly conservative and will only find very strong relationship. And the default parameter is 1. And with 1, you will never overfit your data. It's already conservative. But we can try to reduce it in order to see if we can find a more complex structure without overfitting. And in order to do so, we will just go to validation again. I will go there, tools, cross-validation, and I will use structural coefficient analysis. I can select the learning algorithm I'm using, so I will still use Sublec, and I will just say, yes, I want to try till 0.3, so maximum will be 1, and I will do, I don't know, 25 trials. I will compute the structure versus data ratio. I can also compute data and targets precision if I will, and everything. And now, so we are just building 25 networks with different structural coefficient parameters, just to see the behavior of that learning algorithm with respect to that data. And I can generate curve like that in order to see what is you know, the behavior, the trade-off between the structure and the data ratio. Indeed, here, this is exactly the two parts of my MDL score. My first part is the structure, and the second one is the data ratio. And then the data likelihood, if you want. And then this is the ratio between structural complexity and data likelihood. And if we just use the classical elbow method, we will choose probably structural complexity around that value, here. And we will probably, for example, here, choose 0.45. So I will go there and change my structural coefficient just by right-clicking on the graph panel and select my structural coefficient. And I will set 0.45. Okay, and if I just go back to modeling mode, going through structural Soplec, try to learn, and we just have, it seems, an additional link between Heinz and Emerson Electric. And now we just want to see, to compute, but we'll come back to validation mode and to cross-validation to find, to evaluate the confidence we can have in those arcs. So we go there and we'll compute the arc confidence. And the first thing we can do, we'll just use here the jackknife methods, and we can, for example, say, let's try with, I don't know, 50 tries. So we will generate 50 networks where we will learn indeed on 1400 lines, and we will just remove 30 lines for the learning. So we will, by removing samples from our learning set, we are just introducing some different test sets, some different learning sets, So we are learning those networks. It's quite long. And we will be able to see what, among all those networks that have been generated, what are the confidence we can have on all these arcs. So here we are. I can press on graph there, and we'll see that we have some, you know, the thicker the arc is, the higher is the frequency we found, in which we found that arc. So for example, this one, we found that arc in 88% of the case of the network generated. When we have blue arcs, just means that this is some additional arcs. They were not in the reference structure, but we found them while learning of the structure. We will do the same thing with data perturbation, which is another way to measure. I think it's even better than using the jackknife. We can go there and use data perturbation with 50. And the idea behind data perturbation is just that we are, we are indeed creating a weight associated to each line, and this weight is not 1 anymore, but it's 1 plus a noise. With a random normal distribution with a mean of 0.1, okay? Standard deviation, sorry, of 0.1. So we are just randomizing the weight of each line, and by doing so, we can, by the same thing, generating some different networks. And as we can see, even by adding some noise to that data set, we have highly frequent links. And we can, if we will, just extract, for example, we'll say, well, I will go there, and I will, we can just use, because we have something, we can use that little tool just to see what are the networks that have been generated. So that network is my reference structure, and I can go there. In the first structure have been generated 29 times, and we have that structure. We can go in the second one. This one has been generated 10 times, and this one 3 times, and so on. So we have this kind of information. And as I said at the very beginning, what I want to do there is just to maximize the Markov blanket. So I will just I just see that that node sometimes belongs to the Markov blanket, and in some other tests does not. So I will just select that network just to have the maximum, and I will save that network with that node. It's okay, and I can now. I will just change. I will open that network. I can press P just to have my automatic layout, and I don't have data associated anymore. So I will just show you how we can, given the network, I want to set again to associate again data to that network. So I'm going there, data. It's not open anymore, but associate data source. I would select text file, and then I will select again my sp500.csv. Like that. It's exactly the same wizard, but here I don't have anything to do. I just want to do exactly the same thing, just saying, well, put my data, my original data in my nodes. I just have to say next, next, next. I don't have to define discretization because discretization has already been done, carried out. So I just have to go there. If I want, I can add some nodes, you know, but here it's not the case. So I will just click on finish. And here now my data set is here again. So as you can see, data association, if you don't have anything special to do, is very, very quick. And what I want to do now is to show you how we can use temporization just to analyze those kind of time series. And I will first delete, no, it's not the good one. I will just select Markov blanket there. So I'm clicking on that node, select Markov blanket. So I'm selecting by that contextual menu just the Markov blanket of PNG, and I will again invert the selection, remove the nodes, and I will analyze the time series just with those few nodes. I will remove all the links, and I will select, I will put that here, I will select my nodes and go to Tools, Network Temporization. And I can use that little wizard just to define the number of temporal clones I want to create. So I will create 20 clones. So I'm just clicking here, and now I have a new data set with 21 indeed time steps, and I have my PNG there, t plus 20, and I will learn the relationship of that node with respect to all the other nodes, and I will first define some constraints. So I'm making a right click on that graph panel, and I will define some forbidden arcs. I don't want any connection between my t plus 20 nodes. Okay, and then I will learn a Markov blanket. So it's a supervised learning algorithm just to see what are the relationship of that node with respect to the others. And I can find that network. So that Procter & Gamble at t plus 20 is directly connected. I can go there just to, in validation mode, make a right click in that panel, monitor panel, in order to sort the monitor with respect to that node, and we can see that Procter & Gamble t plus 20 as most correlated variable is t plus 17, and then it's t plus 19, and then it's t plus 10, and then it's Clodot 18, 14, and so on. Okay, so we can. It's not the goal of this webinar to go deeper in the detail, but just to show you how it works. And if I want to do really unsupervised learning among all those time steps, I can just go there, and I will import constraint dictionary, just to say that I don't want any contemporaneous relationship. So I don't want any relationship between my t plus 20 nodes, neither t plus 0, neither t plus 1, and so on. And I will do again a SOPLEC learning algorithm. There. So we are learning also relationship. and I can press P just to activate the automatic layout, removes the comments, and I can, if I want, I can click on my little icon there, my class icon. I will select all the time steps, all the classes for all the time steps, and associate a different color. Like that, I can focus there just to see what is that snake. And as I said during my introduction, it's indeed Kimberley Clark, which is connected to Kimberley Clark T+1. So we can make a compact form of dynamic network here, just to say T plus Kimberley Clark at time t, explain Kimberley Clark at time t+1. Here we have another one, another subnetwork, where with United Technology and PepsiCo, with a relationship between T+1 and T+10, and with T+4 for Clorox. So here I think there is a lot of information. We just have to have a look to them. We have Colgate there, Kellogg, and I guess we have another one, this one for Procter. And I guess we will, as it's 56, I will let Stefan conclude. I don't know, I think we will not have the time to answer directly to the question, but I think, yes, I finished my demo, Stefan.
As we conclude this webinar, I wanted to let everybody know that we will have a recording of this available. So in case some of you joined a little bit late or had to leave early, we will have a complete recording available, and we will share this link with our follow-up email to all the registered participants. Once again, I'd like to remind you of our 3-day seminars that we have coming up in Chicago, LA, Paris, and later in the year in India. If you're interested, most importantly, the deadline for our Chicago seminar is April 5th. So there's still some spaces available, and we invite you to join us. And finally, our next webinar will be on May 5th. That's on microarray analysis, taking us into the field of biostatistics. And as I mentioned earlier, we will have all the answers to our questions. We'll respond to you individually, but we'll also share the general questions with the entire group via our LinkedIn group on LinkedIn. So with that, I'd like to close with referring you to some resources. We have several white papers, tutorials, and book recommendations on our websites. You can either go to conradiscience.com in case you're in North America. For the rest of the world, I'd like to direct you to Bayesian.com. From there, you can download a trial version of BayesiaLab that really allows you to really explore all the features of BayesiaLab, and it's really a highly intuitive piece of software that I really recommend you to try out. And as I said before, we will make the webinar recording available very shortly. So for any remaining questions, I'd like to encourage you to email us, info@conradiscience.com. You can also call us either here in the US, toll-free 1-888-386-8383, or in other parts of the world, country code for France, 33-243-497569. And to make things easy for those in different parts of the world, you can Skype us, and our Skype name, rather intuitively, is Bayesian Network. With that, I think we're perfectly on time. I'd like to thank you all for joining us today. Once again, there was a rather large crowd, and we're very pleased to see such great interest in Bayesian Networks and BayesiaLab. And we hope that we will see you very shortly in one of our upcoming events or webinars. Thanks again, everybody. Thanks, Lionel, for your presentation, and have a great day.